In this screencast, we'll perform a material balance to determine the required volume of one of our inputs in a mixing process. We know the volume and composition of one of the two inputs, and only the composition of the second input, and we need to find the volume. So the second one, composition is 40% by weight. The product needs to have 60% by weight ethanol, and we're also given two specific gravities of the two inputs that we can use to calculate the volume. Now you should stop the video and attempt to solve the problem on your own. To start a material balance problem, it's always important to draw a flowchart of the process, where the box represents the mixer, so our unit operation, and the arrows represent our streams. And of course, a flowchart is useless if we don't actually label it, so we'll put all the information that we have, as well as letters and numbers for the unknowns that we need to calculate. So I'm writing the volume and the composition of the stream, as well as M1 to represent the mass of the stream. And I'll do that for every stream, both inputs and the output. So the unknowns here are V40 and M2, and then we have the rest, the known composition, and here it's M3 and the known composition. Now, before rushing into the calculation part of the problem, it's important to perform a degrees of freedom analysis. Now, what this is subtraction. So we look at the unknowns, the number of unknowns that we have, and we subtract from it the number of independent equations that we can set up. So let's look at how this actually works. So we write unknowns minus independent equations, and there can be three possible results. It can be equal to 0, can be more than 0, or can less than 0. If it's equal to 0, that means we can solve the problem. We have the same number of unknowns as the number of independent equations. But if it's larger than 0, we have more unknowns, which means the problem is underspecified. And if it's less than 0, then the problem is overspecified. And in both these two cases, we can't really solve it. We're either missing some information or the problem is unsolvable. So looking at our case, let's see how many unknowns we have. So we have the masses, so M1 and M2 and M3 are all unknown. And then of course the number we're looking for, which is the volume, V40. So we have 4 unknowns. What are our independent equations? We can set up 2 component balances because we have 2 components in the mixtures. We have ethanol and water. And also we're given the specific gravities. If you remember, it's given us 2 specific gravities which allow us to set 2 equations. So we have 2 components and 2 equations for the specific gravities, SG. Which means our degree of freedom analysis gives us 0, which means the problem can be solved. Now we can go ahead and do the calculations, and first we have to look at what the specific gravity is. The specific gravity is a ratio of the density of a substance over the density of a reference substance, which is almost always water. So we can write it as SG, this is an abbreviation. So SG equals rho of whatever substance we're considering over rho water. So that means using specific gravity, we can always find the density of a substance and then use it to convert volumes into mass and vice versa. So in our case, for the first input called SG1, we know that that's 0.877, and it's a rho of 1 over rho of water, which is always 1,000 kilograms per meters cubed, which means that the rho 1 is 0.877 times 1,000 kilograms per meters cubed, which is 877 kilograms per meters cubed. This allows us to use the density found to convert that volume, the 500 liters, into the mass M1. We divide 500 by 1,000 to convert liters to meters cubed. And then we can multiply by the density to obtain the mass in kilograms. So 877 kilograms are equivalent to a meter cube of this substance, and the result is 438.5 kilograms. Now we can make use of the material balances to find M2. So let's start with an overall material balance. This looks at the total amount of material per stream. So M1 and M2 and M3, where M1 plus M2 equals M3. Input equals output. Material is always conserved mass. So after that, we can look at a component balance. We can choose ethanol or water. Let's go with ethanol. And this, as opposed to the overall balance, and the component balance looks more specifically at the amount of ethanol per stream. If we look at the flowchart, we see that we had 0.75 ethanol in M1, 0.40 in M2, and 0.60 in M3, which means that 0.75 M1 plus 0.4 M2 equals 0.6 M3. Solving these two equations simultaneously gives us M2. So these two lines of working, of calculations, lead us to find M2, knowing that M1 was 438.5 kilograms, M2 is 328.9. We found the mass of that input, but the problem asked us to find the required volume for the mixture. So we're gonna have to use specific gravity again to find the density of that mixture. So knowing that the specific gravity of that stream is 0.952, this means that the rho, the density of that input, is 952 kilograms per meters cubed. And the volume V40 is just mass M2 divided by the density ρ2, and we find that it's 0.345 meters cubed, which is the same as 345 liters.